So I'm going to present some work on approximate Bayesian analysis for unconditional or conditional copulas. I will introduce briefly the unconditional version, and then I will show that the conditional version is much more difficult to analyze. And I'll try to present several steps we have done and several approaches we have proposed to work in this setting. And I would like to acknowledge also my collaborators. This work has been founded by the Royal Statistical Society, and it's jointly with Luciana Dalla Valle from Plymouth and Brunero Diseo from Sapienza in Rome. So, just to give an introduction of copulas, a copula model is a general way of representing unjoined distribution. So given a divariate cumulative distribution function, and several marginals, we can define any joint distribution in terms of a copula function which takes value from the marginal distributions. So this is a very nice representation and a quite important result. Also, like if the variables are continuous, it can be shown that this representation is unique. Because a copula, so if we take the density, so again, if the distribution function, the multivariate distribution function admits a density, it is easy to show that this density will be defined as the product of the marginals times the density of the copula function. And so the copula function is what really absorbs of the dependent structure of the multivariate distribution. However, this result is important, but it's not constructive. So it tells you that this representation exists, but it doesn't tell you what is this representation. And in the literature, there are several copula functions that have been proposed. Like some of the famous ones are the Clayton copula, the Gamble copula, the Frank copula. But each of these, so another are the elliptical copulas coming from generalization of the Gaussian and the TD distribution. So what I would like to notice is that if you choose a particular copula function, maybe you can model the data in a more flexible way with a structure of dependence more complicated than standard multivariate joint distributions. However, you're still making a strong assumption on the type of the dependence. So, for example, if you use a Clayton copula, it means that you're assuming that there is more stronger dependence on the left tail than on the right tail, while a Gamble copula has a strong dependence on both sides, for example. So choosing a copula is a pretty important assumption when you try to model the joint distribution. There are several methods proposed in the literature to estimate copula models. And when I say copula models, I mean, you fix a copula and then you try to estimate the parameters. In a frequentist setting, the most used method is the inference from the margins. So you first estimate the parameter of the marginal distributions, then you plug these estimates in the joint distribution, in the copula representation, and then you estimate the parameter of the copula model. And it can be proved that if you do that through maximum likelihood, this can be unbiased in most situations. Another method is the method of moments, and so you relate the parameters to some quantities of some measures of dependence, like correlation measures, and then you estimate those correlation measures, for example, the Spearman's law or the Kendall's law, and then you transform those measures into the parameter of the copula. In a Bayesian setting, there are some proposals. So let's say that if you have a likelihood and a likelihood function, so if you choose a copula model, then the problem is pretty standard. However, there are some interesting points, and in particular, like high-dimensional problems can be extremely slow in terms of computation. So arriving to the estimates can be extremely slow. And so there are some ways to simplify the methods. One of these way is to use Gaussian copulas when you just use bivariate conditional copulas. So you split the problem into conditional copulas, and then you have to estimate only like bivariate copulas. However, like again, like the dimension of the problem tends to be a pretty important aspect of the estimation process in a Bayesian approach. So in general, like the likelihood function can be written, but it tends to be complicated. So if you want to approximate the posterior distribution of the parameters, it could be expensive computationally, it could be tricky. In particular, if you are interested in some functional of the dependence. So in many cases, you're not interested actually in the parameter of the copula function, but you're interested in some functional of interest. So in some cases, you can just transform this parameter, so there is a direct relationship, but in some other cases, the relationship is more complicated. And so sometimes you would like to just estimate these functionals or having a posterior distribution for these functionals without introducing a copula function. So what I'm going to propose today is a set of algorithms which can be read in the class of approximate Bayesian computation. So there are, like, I know that it's a class pretty known, and there are several people working in Warwick about in this field. Just to recap, like there are several types of algorithms within this class. Like the most famous one probably is the rejection ABC, where you fix some summary statistics and then you simulate. So you substitute the evaluation of the likelihood with simulations from it. So you simulate from the model, then you compute some summary statistics, and you try to so you accept those parameters leading to summary statistics close to the one you observe on the data set. But there are other ways, so other algorithms within this class, more based on an approximation of the likelihood. So you don't evaluate the likelihood, but you approximate it. And so you can use the simulation from the likelihood, or you cannot use it. One method, for example, is to approximate the distribution of the distance measure between summary statistics. Other methods use approximation of the likelihood, like a synthetic likelihood and empirical likelihood. And one of the techniques I will present today is based on the empirical likelihood. So during my PhD, actually, I worked on the development of an algorithm to approximate the posterior distribution of a functional of the dependence by using an empirical likelihood approach. Instead of using, so the empirical likelihood is a way to produce a non-parametric likelihood for a parameter of interest. Instead of using the classic definition of the empirical likelihood due to Owen, we decided to use the exponentially tilting empirical likelihood proposed by Shennock because it has directly Bayesian representation. So instead of using a maximization problem, so relative to the weights, only the weights, this exponentially tilting empirical likelihood uses a maximization problem relative to the entropy of a distribution. So, as I said, we decided to use this type of empirical likelihood because it has a Bayesian representation. In particular, if I want the posterior distribution of a functional of interest, phi, I can see that as an integral with respect to an additional parameter of the distribution. So in the particular case of copula functions, if I'm interested only in the posterior distribution for a functional of the dependence, but I don't want to introduce the copula, what is my additional parameter of the copula is the rest of the dependence. So I'm just focusing on the functional of the dependence of interest, and then I consider all the rest of the copula, so all the rest of the dependent structure, as nuisance parameter. And it can be proved that the exponentially tilted empirical likelihood can be seen as an integrated likelihood where the prior for these additional parameters representing the copula, so this C star parameter belonging to an infinite dimensional metric space, is a type of distributions where you try to maximize the entropy of this discretization of this parameter, which are just a discretization of the entire space. What we proposed was to, so we developed this algorithm where we had to select a quantity of interest and give it a prior distribution. For example, if we are interested in the Spearman's law, we can give a prior distribution which can be a uniform distribution between -1 and 1. In general, these functionals of the dependence are defined in a compass space, so defining a distribution tends to be easy. Then we needed to select a non-parametric estimator of this quantity of interest, and for the Spearman's law, a consistent non-parametric estimator exists. Then we can compute the empirical likelihood for this functional and combine that with the prior distribution to obtain an approximation of the posterior distribution. We've proved that this algorithm has several good properties, and it seems to work. Now, we would like to extend this to the case of conditional copulas. So, conditional copulas, I think I can, okay. Conditional copulas are just an extension of unconditional copulas, and this extension in presence of covariates is just given in the same way. So so the copula is defined conditionally on the covariate, and each marginal has to be defined conditionally on the covariate. It has also been shown by Patton that this conditioning on both the copula and the marginal is necessary to avoid some biases in the representation. So it seems an easy problem, so it's just a natural extension, but then the problem of estimating the parameters become much more difficult. So there have been some parametric, so like the main problem becomes, so the main proposal, the main type of approach in this case is to define, instead of defining the copula itself as depending on the dependent structure, you just define the parameter of the copula as depending on the covariate, and then you can define, you can estimate these parameter parametrically or non-parametrically in a Bayesian or in a non-Bayesian way. Another way to treat the problem, of course, this is a much easier problem because you just have to estimate a parameter depending on some covariate. Another easy solution is to use the simplifying assumption and trying to work with like forms of independence in the joint distribution. There is also a way to work in a non-parametric Bayesian way to estimate the full conditional copulas through Dirichlet processes. But again, if we want to estimate, so if the interest of the analysis is in a functional of the dependence, this given definition of this function in terms of the covariate are easy, and we can still define them with respect to the copula. However, and so the easy thing to do would be to find estimators of these functionals depending on an estimator of the copula function. And so if we want just to apply the approximate Bayesian algorithm I briefly showed before, we should just use estimator like estimators of these quantities based on an estimator of the conditional copula. And this is a simple extension of the empirical copula, where these weights are some weights smoothing over the covariate space. For example, the Nadaraya Watson weights or the local linear weights, depending on some bandwidth. So it's a usual representation. However, one of the problems, so again, I'm just showing these weights because I will use them in the following. So I just use this, and then of course you have to choose also a kernel, and what we will use in the following are both the Gaussian kernel and our tri-weight kernel. So although this copula estimator seems pretty standard, and it seems just an extension of the unconditional copula, if we just look at its definition again, it can happen that you have larger values of y1 at the same time as larger values of y2, only because they are both correlated to larger values of x. And so this can create an artificial dependence between y1 and y2. And it means that this estimator is biased. It's also been, so this is just to give roughly idea of why it is biased, but it is possible to mathematically prove it. There is another proposal for the estimator of the copula by Gibbles and co-authors, but also that, so they also prove that that estimator is biased. The difference is that they show that the second estimator can reduce the bias in some situations, while the first estimator seems to have less bias in other situations. So it's difficult. So there hasn't been proposed an estimator of the conditional copula which is at least consistent. So if we want just to apply, so one of the main points of the empirical likelihood is that we need to have a moment condition which is respected, and so we need to have a consistent estimator respecting this this condition, this moment condition. So if we just want to apply the algorithm I showed before on the conditional version, for example, of the Spearman rho, what happened is that the accuracy of the estimate really depends on all the parameters of the weights. So for example, here, like the top two figures are based on the Nadaraya Watson weight. And this is the tri-weight, this is the Gaussian kernel, and these two are based on the local linear weight, and again, this is the tri-weight kernel, and this is the Gaussian kernel. So you can see that if I use a almost linear function of the rho, what I get, so these are the yellow dashed line represent the frequentist estimate, yes, and then the dotted blue line, the Bayesian posterior mean, and then the intervals. So you can see that what we get is actually something that follows strictly the frequentist estimate, and it can be better or worse depending on the type of weight you choose and the type of kernel you choose. And of course, in this case, we can see that, for example, this seems to behave better But in general situation, you don't know what the truth is, so you don't know exactly how to choose it. Of course, you can always choose, try to choose through cross-validation or something. So all the parameters and all the weight through cross-validation. But again, like you will like something like more general. And like, for example, the parameters in these 4 pictures have been changed. So, for example, the bandwidth have been changed, something, but more or less, it's difficult to find a way to choose exactly what the parameters of your estimator. And if we go to a slightly more complicated function, so here I'm representing the rho as a same function. You can see that again, like some estimators are much worse than others. But again, like in this case, like this estimator seems to work better, while in this case, this estimator seems to work better. And we would like something that works better, like on average. So our first proposal was to try to rephrase the problem, and so I'm trying to use like normal variables instead of directly trying to work on the functional of interest. So to encourage normality, we use a transformation of the functional through the Fisher's transform. And what we actually, so we thought that, so we have to assume that this variable depends on the true value of the conditional rho. But then what we observe is a noisy version of it due to the fact that we use the estimator of the conditional rho, and this is a biased estimator. Now, we can suppose that the variable z, which is associated with the true rho, follows a priori a Gaussian process, and the Gaussian process can depend on some parameters in the location and in the covariance structure. So, for example, common choices. So these are some bases, and common choices are, again, we can use a location which is 0, or we can use some locations depending on the covariance itself or any expansion of the covariance. While for the covariance structure, we can use the standard kernels for using Gaussian processes. So, for example, we can use a kernel depending on the distance between values of the covariance space, like, for example, the square exponential kernel. Now, we assume that, as I said, we don't observe values of, so we don't observe, clearly, we don't observe directly Z, but we observe a noisy version of it, which depends on a statistic evaluated at location X. Now, we can make assumption on the type of noisiness. We can, for example, assume that there are compensating errors, and this can be modeled through a Gaussian distribution. This error term can, like these error terms, depending on like different values of the covariate, can be independent or can be dependent. Of course, this is an easy representation, but you can also like define these variance as a function of the covariate itself, for example, to create a more flexible model or a more realistic model. Of course, if you assume some Gaussianity, there are some forms of compensating errors. So this is still an assumption. And then, like, to speed up the computations, instead of using directly the Gaussian process, we decided to use a version. So, like, we decided to focus on an integrated likelihood of the parameters. So we decided to use a reparametrization of the likelihood, the parameters of the likelihood, so that we can use, we can focus on less parameters during the MCMC step, while this S is a variable depending on the observations and some type of projection matrix. Then, so all the problem becomes a parametric problem, and so we can define a posterior distribution, and we can approximate a posterior distribution for these parameters. And then to predict values of W on new locations, we can just integrate the complete, the joint distribution of the prediction and the parameters with respect to the parameters. And so we can just obtain a sample for the prediction in the standard Bayesian way. And of course, if we are interested not in this Fisher's transform, but on the functional, we can then obtain a posterior distribution of the functional itself. So now if we follow, so if we go back to the example of the rho as a linear function or as a sin function, you can see that like these red dots are the frequentist estimate for each level of the covariate, and then we have, and the blue line is, sorry, the black line is the truth with points like the true point in the covariate level. So we can see that one of the good thing that seems to happen is that the approximation seems to be good. So these are just the cases, but we have run a full simulation study and the approximation seems good. One of the problem of this approach is that if you have to estimate well, one of the probably pitfall more than problem of this approach is that you have to define, you have to have an estimator for each level of covariate. So you have to, sorry, where is that? Here. So you have to have an estimate for each level of the covariate you get. So it means that you need to have repetitions for each covariate of the observations. So you have to fix the level of the covariate and have repetitions for that level of the covariate. And this may not be always available. So if this is true, then this Gaussian process model seems to work pretty well in representing, in following the curve we have considered. Of course, another disadvantage is that there are some assumptions of normality. There are some assumptions of on the errors of what we observe. So we are not assuming that we observe. So what we observe is always biased in the same direction with respect to the truth, and we are assuming some types of regularity of the function itself. So the assumption of normality may be sometimes too strict. So we would like to use a fully non-parametric approach along the line of the ABC algorithm I showed you before, but which allows to use consistent estimators to make it possible to have moment conditions which are respected in the application of the empirical likelihood. So instead of using like a Gaussian process of the Fisher transform, we can use the Fisher transform of the observation as a function of some covariates through some sort of expansions, for example, the Taylor's expansion. And so we have a polynomial representation of this Fisher transform. And then we have a sort of regression model, and we can have a consistent estimator for the parameter beta of this model. Alternatively, it is also possible to use a cubic spline instead, or another type of spline. And again, like the problem becomes estimating alpha, and so both alpha and the knots of the spline can be used, can be considered as parameters, and we can have consistent estimator of this two type of parameters. So we can apply the empirical likelihood in these two type of problems. So what you get is that you will have some simulations of the parameters. So for example, if we just use a polynomial expansion, we have a set of betas simulated from the prior, and then to each set of betas we just relate weight coming from the empirical likelihood. And then the predictive distribution is just obtained as it's a sum over all the simulated parameters betas and weighted for the weights given by the empirical likelihood. One of the problem with this is, again, it is really problem specific. So it is easy. So this model is very non-parametric, and it's easy to, because you are approximating non-parametric. So you are estimating non-parametric likelihood of a model which is already a non-parametric representation. So what you can get is that the estimate of the beta parameters are not extremely concentrated. And so when you just use the weights, and so when you combine these, so when you get this estimate and then you use the transformation to go back to the raw, the uncertainty is pretty high, and so more or less the uncertainty covers all the parameter space. However, so these are more or less all the approaches. But one of the points is that choosing the copula is pretty difficult. We have run simulations with 4 main copulas and used several approaches to choose the copula. The Clayton copula seem the best to be recognized. However, other copulas, in particular the Frank, can be pretty difficult to select. And so far, the main proposal in the literature are based on the selection of the copula and then estimating the functionals depending on the copula you have selected. But as I said, selecting the copula is pretty difficult, mainly because the differences tend to be at the tail of the distributions, where exactly you have less observations. So I have not too much time left, so I would like to probably skip this energy example, and I'll go directly to the magic dataset, which I like more. So we had data which are actually generated through Monte Carlo simulation for high energy gamma particles from the Cherenkov Gamma telescope. So what the telescope does is observing high energy gamma rays, taking advantage of some radiation. So when you have an event, it gets some radiation, it produces some radiation which interact with the particles, and this creates electromagnetic events as well, which were initiated by gamma rays. So the goal of this in this set of problem is to discriminate statistically the electromagnetic events coming from gamma rays from coming from other cosmic rays. And so it's more or less a problem of classification. And what you do is actually studying some pictures, some images, and you study the form of these images. You tend to have ellipses, and so you study the form of these ellipses, and it could be the axis of the ellipsis, it could be like other type of form. And this can help in understanding the derivation of the, so which type of rays produce the what you are observing. It's interesting to see that actually, so I'm just comparing, so I'm just focusing on a bivariate problem, looking at the major axis of the ellipsis recorded, and this is something related to the third moment of the axis. And so it's interesting to see that the joint distribution of these two quantities is particularly strange, so it has this strange form, and the type of dependence of this variable seems to be really difficult, like really strange. So what we did was to actually use several all these approaches, and these are the results obtained through the Gaussian processes, which were more regular. You can see that the Spearman's rho seems to like have an increase at the beginning of the covariate level, and then have a drop, and the same type from so this is the size of the pixel of the what you see in the pixel of the image, and this is the width of the ellipsis. And so you can see that, so this is a case where you can have a repetitions in several levels of size and width, so the Gaussian processes seems to work well. At least it seems to be regular. In this particular case, the other approaches produces a very high uncertainty on the estimate. But this is not necessarily true. So, for example, in the previous example, I didn't show. Like these are the results for the spline, so it seems to be pretty not following really what is observed. But other approaches, like based on other, so for example, on a theorem expansions, it seems to produce like more regular results. So just to conclude, so I proposed several approaches to tackle the problem of estimating functional of the dependence, like when using copula models. These all of them are based on a non-parametric version of the copula, so we don't want to assume a particular function for the copula, and this is made mainly due to the fact that selecting the copula is difficult. It can be easily extended to any dimension of the observations. Computations for each of these methods are very fast. And also for different dimension of the covariates. Of course, if the number of covariates increases, these are methods that tend to become slower. And in some cases, for example, in the Gaussian process, you should have repetitions for each combination of covariates. So you cannot really think to have a large number of covariates for which this is true. It can be generalized to any function of the dependence, so not only the Spearman's rho, but also tail dependence coefficients. It's easy doable. And of course, there are some drawbacks. So, for example, for the first algorithm, you need to choose some types of moment conditions, which has to be respected. While the GP approach needs replication, and maybe not all the problems have it. So I think I conclude here. I leave some bibliography, and I'm happy to answer to any question you may have.